Okay, today's starter. Here's the situation. I give you a crate, a 50 kilogram crate on wheels. There's no friction on a horizontal flat surface. It's going to start from rest, and this force is going to push this crate through a displacement of 5 meters. I want to know what is the acceleration and what is the final velocity. And these two, A and B, I want you to use kinematics. And well, this is Newton's second law, and then kinematics to solve it. And then this is a kind of a review of what we did last time, where we have work and change in kinetic energy, and then using energy to find the final velocity. And so if you're watching this at home or on video, please pause the video and work the problem right now. Okay, let's solve it. So A is pretty easy. And now I can go ahead and go through a rigorous process of drawing the free body diagram. I've got gravity pulling it down. I've got a normal force with the wheels pushing up on it, but there's no friction. These don't really have anything to do with the problem. We have this force, this pushing force like this, and this applied force, that is the net force. If I sum the forces in the x direction equals ma in the x direction, we'll call this x and this y. Well, then there's only one force in the x direction, and that's F equals ma. And most of you probably started there, but I'm just being super rigorous. So the acceleration is equal to force divided by the mass, and the force pushing on it was 100 newtons. Divide that by the mass. The mass is 50 kilograms. 100 divided by 50 is 2. A newton per kilogram gives us a meter per second squared. So that's the answer for part A. Now part B, well, to use kinematics, notice that I don't have time, but I know the initial velocity. I'm trying to find the final velocity. I know what the displacement is, and now I know what the acceleration is. So I'm going to use the fourth kinematic equation, which is the final velocity squared equals the initial velocity squared plus twice the acceleration times the change in position, displacement. This is given to be 0. So if I solve this for, well, it's already solved for v. So v equals the square root of 2a delta x. See, I'm just taking the square root of both sides. And so that v is equal to the square root of 2 times 2 meters per second squared times 5 meters. Well, that's 4 times 5 is 20. The square root of 20. I get 4.47. Anybody else get that? Get that far? Good. Now we're going to do part C, and this is the new stuff. See, this is all review. But for part C, the work done, well, work equals force times displacement times the cosine of the angle between the force and the displacement. Well, the force was 100 newtons. The displacement is delta x, that's 5 meters. And if you look at the picture, the force is to the right and the displacement is to the right. So the angle is 0. So you can put cosine of 0 degrees if you want to, but what is the cosine of 0? It's 1, so it's just 100 times 5. So the work done is 500, and a newton times a meter is a joule of energy. Then D, well, look, this force right here, you can see on the free body diagram, that's the net force. Pay attention to me. But this is the net force. And the work done by the net force is equal to the change in kinetic energy of your system. That's the work energy theorem that we developed last time. Well, Therefore, the work done by the net force, we just got it, is 500 joules. So that's my change in kinetic energy. So that was really easy. And then finally, part E. Well, delta K is K final minus K initial equals 500 joules. Well, K final is 1/2 mv squared minus K initial, but K initial is 0. The initial velocity is 0, so I'll just put minus 0. Now, this lets me solve for V. So I'm going to solve for V. This is just kind of zeroed here. So V squared equals 2 times 500 joules. And then we're going to divide by the mass, which is 50 kilograms. And then to get V, I just need to take the square root of that. And so, let's do this. 2 times 500. Well, actually, this is 500. What's 500 divided by 50? That's 10. What is 2 times 10? 20. What's the square root of 20? 4.47. So this is the same answer that we got in part B, which makes a lot of sense. It should be the same answer. So here's the whole problem. If we can get it all on screen. This up a little bit. So look, if you compare this, which method is easier to find the final velocity? Well, they're both pretty easy, but in a lot of cases, if what they're asking for is the final velocity, using energy is the best way to go, using the work energy theorem or energy methods. Any questions? Okay, that is all.